Okay. So welcome everyone. Just let me know if my audio is clear. I think we had this problem last time. Good evening. Just let me know if my audio is clear. Is my audio clear? Is my audio clear? Just give me a confirmation if the audio is clear. Okay. Okay. Thank you and thanks for the confirmation. So okay. So audio is clear or not? I'm getting both kind of messages. Just let me know if the audio is clear. Okay, so we'll start with the third session of this GATE Champion series for GATE 2025. Okay, so yeah, we'll proceed. Like I've told in the previous two sessions, we have discussed about the representation of numbers, that is the base conversion of numbers as well as signed number representation. And in the second session, we have discussed about another important topic, K-map minimization. Now, in this session, we will discuss, one of the most important topics in digital electronics, which is logic gates. And in today's session, I will explain you one method where we can, analyze the problems on logic gates in a very logical manner. Okay, so if you follow this approach that I discussed today, I'm pretty sure that any question on logic gates you can easily solve it. Okay, but yeah, one prerequisite for this topic is you have to know the min terms, max terms representation of function. Okay, so this is something that I'm expecting out of you already. So min term, max term representation of function is very important for you. Okay, so once that is clear, then definitely we can proceed further. Yeah. And in this topic of logic gates, what to learn as well as what to remember. There are a few topics that you have to remember for all logic gates. That is mandatory. You can't escape from that. Yeah. The first is nothing but functionality. For every logic gate, you have to obviously know the functionality. And whenever I say functionality, I mean to say functionality in terms of two methods. One is by means of truth table. Most of the people will only study the truth table and they'll ignore the other part. You also have to know the functionality in the form of a statement. Okay, so functionality of every logic gate in the form of a statement also you should know. If you know that, analysis becomes much simpler and much easier. Okay, the next topic is basic identities. For every logic you have to know what will happen whenever one of the input is 1, one of the input is 0, when both inputs are same and when both inputs are complements of each other. So we can call them as basic identities. We have earlier questions based on purely basic identities also. Okay, so but nevertheless we have got those questions in computer science branch, but still we have got the questions in the previous years. Okay, then next, after that you have to know the properties. Properties, it is important because we have got earlier direct questions on properties. Okay, not just in GATE exam, but also in other exams like GATE, IES, ISRO, BARC, etc. We have got direct question on properties, and hence you also have to know the properties of every logic gate. And lastly, what will happen whenever you have a n input scenario? Okay, so whenever you have a n input each logic gate, what will happen? That is again something that you are supposed to know. Lastly, this is what is very important. Okay, this is something that many people don't discuss also in classes. Okay, what happens whenever the inputs of logic gates are in the form of functions instead of variables? Usually, variables will be given as inputs to the function logic gates. Sometimes what they do is they also specify the inputs in the form of functions. Even though the question is not about input in the form of a function, sometimes whenever you solve problems, if you understand this approach, it becomes very easy for you to solve the problem. So this is what I was telling earlier. I will be focusing this session mainly on this point. Okay, so today's session is all about how to solve logic gate questions by using this approach, which we will discuss towards the end of the logic gate discussion. Okay, yeah. So let us have a basic idea regarding all logic gates. Very briefly, very quickly, we will cover all the logic gates, starting with OR gate. So this is the logic symbol of OR gate. So if the inputs of OR gate are A, comma B, the output is nothing but logical addition of both A and B. So here in OR gate we are performing addition. What kind of addition? We are performing logical addition. Okay. So it performs logical addition. Or we can also call this logical addition as Boolean addition, or also known as Boolean addition. Okay. And the functionality in the form of statement is nothing but whenever one of the input is 1. Okay, please notice whenever one of the input is 1, at least one input is 1, means definitely output becomes equal to 1. And only when all inputs are 0, only then output becomes equal to 0. So this is the truth table. Here you can observe that even if one of the input is nothing but 1, output became equal to 1. Output became equal to 1. And only when all inputs are 0, output became equal to 0. Okay. And coming to the properties, OR gate satisfies both symmetric as well as associative properties. In the sense that A plus B is also equal to B plus A, and associative property says that A plus B plus C is also equal to A plus B plus C. So here the order of variables for a particular logic gate is irrelevant. In the second case, the order of operation is irrelevant. Okay, so first I am performing OR operation on BC, and the result of that is OR with A input. Here I am doing slightly reverse. So initially I am performing logical addition of A comma B, and the output of which is given as input to another logic gate whose other input is nothing but C. Okay, and this is also same as the input to a 3-input gate. 3-input gate, we put ABC in one single bracket, means we are having a 3-input logic gate. Okay, and coming to the basic identities of OR gate, when one of the input is nothing but 0, basic identities are one of the input is 0, one of the input is 1, one of the inputs are same, and inputs are complements of each other. Okay, so whenever one of the input is nothing but 0, A plus 0 becomes equal to A plus 1 becomes equal to 1, because one of the input is 1. In OR gate, one of the input is nothing but 1, output automatically becomes 1. A plus A by means of idempotent law becomes equal to A plus A bar. So whenever you have A plus A bar, at least one of the input is nothing but 1. So if A is 1, yeah, output anyway is 1. If A is 0, A bar becomes 1 and hence output becomes equal to 1. Okay. So these are the basic identities in case of OR gate. Next we have AND gate. AND gate function in the form of statement is nothing but output is 0 when at least one input is 0. Okay. So when at least one input is 0, output becomes equal to 0. And only when all inputs are 1, output becomes equal to 1. Okay. So only when all inputs are 1, that is when output becomes equal to 1. Okay. You can observe the same thing here. So when at least one 0 you are having. I'm having a 0 here, I'm having a 0 here, I'm having at least one 0 here, and hence output became equal to 0. Only when all inputs are 1s, output is equal to 1. And even AND gate satisfies the associative property, which simply says that A into B becomes equal to B into A. Okay. And it is also associative, which says that A into BC also becomes equal to AB into C, which is also equal to 3 input AND function. Okay, which is also equal to 3 input AND function. And coming to basic identities, A into 0 is 0 because we are having at least one 0 and hence output is 0. A into 1 becomes equal to A, which is basically the identity property, and A into A becomes equal to A, idempotent law. And lastly, A into A bar becomes 0 because at least one of the input here becomes 0. If A is 0, output is 0. If A is 1, A bar is 0 and hence output is also 0. Okay. So this is regarding the second gate AND gate. Third, we are having NOR gate. NOR is the complement of OR simply. So we have a bubble here. The bubble here indicates that complement function. So this bubble corresponds to complementation functionality. So functionality wise, NOR is complement of OR. And the logic symbol is nothing but complement of OR means A plus B whole bar. A plus B is OR operation, and complement of that is nothing but A plus B whole bar. And like I have told, NOR is always equal to complement of, basically complement of. Okay. And since it is A plus B whole bar, functionality in the form of a statement is, even if you are having at least one input which is 1, okay, the inputs, if at least one input is nothing but 1, then output straight away becomes 0. Okay, so at least one you are having as input means straight away, irrespective of other inputs, output becomes equal to 0. Only when all inputs are zeros, only when all inputs are zeros, that is when output becomes equal to 1. So only when all inputs are zeros, that is when output becomes equal to 1. And NOR gate is symmetric but not associative. Okay. So yeah, A plus B whole bar is also equal to B plus A whole bar. So if I reverse the inputs to a particular NOR gate, the result is exactly the same. But if I reverse the order of operations on the variables, then I won't get that same function. And hence, A plus B plus C whole bar is not same as A plus B whole bar plus C whole bar is not same as 3 input NOR function. So whatever you see here, this is basically 3 input. This is basically 3 input NOR function. Okay. Next, coming to the basic identities. The basic identities here will be exactly complement of what we had in the case of OR function. When one of the input is 0. Okay, so in that case, the NOR gate functions as NOR gate. And when one of the input is 1, like I told earlier, at least one means output is straight away 0. I don't even care what is the other input, output straight away becomes 0 when one of the input is nothing but 1. Okay, and when both inputs are same, NOR gate functions as NOT gate. Okay, and hence if you see, the variable A is complemented on the output side. And when inputs are complementary, we are having at least one input which is 1 and hence output becomes equal to 0. So this is one logic that we can use in order to implement NOT functionality by using NOR gate. So there are two ways in which you can implement NOT gates by means of NOR gates, very commonly asked in exam. Okay, so I am taking NOR gate. Yeah, one of the input can be, let's assume A, but the other input is 0. So in that case, output is basically A bar. So means whichever input that we have connected here, is being complemented on the output side. Next configuration is very commonly used in order to use NOR gate as a NOT operation or NOT gate operation. So whenever you short both of the inputs, then your NOR gate functions as a NOT gate. In fact, same thing happens even in the case of NAND gate. So in NOR gate, NAND gate, when inputs are shorted, in that case, the NOR gate as well as NAND gate functions as a NOT gate. So if input is A, output is A bar, just like a NOT gate operation. Okay. Yeah. Next we have NAND gate. NAND, just like in the case of NOR, is also not associative. Yeah, it is symmetric but rather not associative. In the sense that whenever you change the order of operations, the output is not 1 and the same. Okay, so hence A into BC bar whole bar becomes is not equal to AB whole bar into C whole bar is not same as 3 input NAND operation. Okay, so yeah, again here also you have a bubble. So the bubble here corresponds to what? NOT operation. Whenever you see this bubble corresponds to this bubble indicates NOT operation. Okay, and the logic equation is nothing but multiply both the inputs and then complement the multiplied result. And here again, the functionality in the form of a statement is even if one of the input is 0, output is 1. So you are having at least one input as nothing but 0, means output becomes equal to 1. And only when all inputs are 1s, output becomes equal to 0. That's what we have here. Only when all inputs are 1s, output is 0. I am having at least one 0, means output obviously is 1. Okay. And the basic identity is complement as compared to what we had in the case of the AND operation. Here again, there are two areas where NAND gate can function as basically NOT gate. Do remember these configurations, because the moment you identify that in the exam paper, now it becomes very easy for you to analyze. Okay. Yeah. First case, one of the input for a NAND gate is nothing but this is NAND gate, and one of the input is basically equal to 1. Okay. So then the other input is complement. Or for a NAND gate, whenever you complement or short both the inputs, okay, shorted both the inputs. So both inputs are 1 and the same. If one input is A, the other input is also equal to A. So then what is the value of output? The value of output is nothing but A bar. This configuration as well as in NOR, this configuration. Okay, so NOR as well as NAND, when you short both the inputs, the corresponding gate functions as a NOT. Okay, so this is regarding the 4 basic logic gates which are AND or NAND. Then we have XOR gate. So the XOR gate logical expression is given like this: a plus symbol inside a circle, and XOR gate performs arithmetic addition. Okay, so it performs arithmetic addition. See, XOR and OR both perform addition only. XOR performs arithmetic addition, whereas OR gate performs logical addition. Both are not one and the same. Arithmetic addition is basically adding the number, and there we are actually, in case of logical OR operation, we are logically adding the numbers. Here we are arithmetically adding the numbers. Okay. So yeah, whenever we want to understand the XOR gate in the form of a statement, yeah, it is simply counting the number of ones. XOR, XNOR both simply counts the number of ones. Only number of ones, not number of zeros. Okay. So whenever there's a small mistake. This should be 1. They are simply counting the number of ones. So output is 1 whenever the number of ones at the input side is nothing but odd number, and output is 0 whenever the number of ones at the input side is nothing but even number. So odd number of ones means 1, even number of ones means 0. So that is what you can see here. I'm sorry. Okay. So here I am having even number of ones, I am having 0 ones, and hence output is nothing but 0. And in these two cases, the number of ones you are having is nothing but 1 odd number, and hence output is equal to 1. And here if you notice, the number of ones is 2, even number. Even number means output is 0. So even number of ones, output is 0, odd number of ones, output is 1. Okay. And the equation of this particular XOR function can be written as, this equation is pretty common, pretty important to remember also for you. This will be written as A bar B plus A B bar. Basically, we are these two minterms. The ones in the function corresponds to minterms, and hence we can express A XOR B as nothing but A bar B plus A B bar. Do remember it, very important. Okay. And if you want to write this in terms of max terms format, max terms corresponds to the zeros. The first 0 can be written as what? Since both of the inputs are zeros, we can write it as A plus B. And the next 0, which corresponds to AB11, can be written as A bar plus B. Okay. So this is basically the equation of XOR. And coming to basic identities of XOR are very important. When one of the input is nothing but 0, XOR gate functions as buffer gate. And how can you derive this? You can derive it like this: A XOR 0. According to this formula is basically A bar into 0 plus A into 0 bar. Okay, so what is anything into 0? 0 only. So the first term is 0. What about the second term? A into 0 bar. 0 bar is basically 1. So we can write it as A into 1, and hence answer is A. Answer is A. That's what we have obtained there. But do remember it like this, that whenever in XOR gate one of the input is 0, it functions as buffer gate. And whenever one of the input is 1, it functions as NOT gate. That is A XOR 1 becomes, according to this formula, as what? This is A bar into 1 plus A into 1 bar. And what is anything into 1? The term as such, A bar only. What about the second term? We have 1 bar here. 1 bar means 0. Anything into 0 is 0 itself. So A bar plus 0 becomes how much? It becomes equal to A bar. So if you want to prove any of these basic identities, you can always use the basic formula in case of XOR function. This formula is very commonly used, very commonly used in problems. Okay. Next, coming to the XNOR function. So XNOR, do remember it like this. This is basically complement of XOR. Okay. So this is always complement of XOR. Right? And hence, this guy is also counting the number of ones only. And whenever the number of ones is odd number, so then output is 0. And whenever the number of ones is even number, so in that case, output becomes equal to 1. So here, whenever the number of ones at the input side is nothing but odd number, so in that case output becomes equal to 0 here. And whenever the number of ones at the input side is even number means output becomes equal to 1. So in this case output becomes, okay, small correction has to be made here. Again, count the number of ones here. We don't have any ones, 0 ones. 0 is even number means output is 1. In these two cases, we are having odd number of ones, output is 0. And in the last case, we are having 2 ones, output is obviously because of that 1. Okay, so this is in case of XNOR function. And XNOR is symmetric but not associative fully. Okay, it's not completely associative. If you notice, there is an equality here, and furthermore, there is an inequality on the other. So XNOR function is not fully associative. Okay, please notice this. It is not fully associative. So A XOR B XOR C is also same as A XOR B XOR C, but not same as this guy, which is a 3 input, not same as 3 input XOR function. 3 input XNOR function. Okay. So then what are these guys? These basically later on we will show becomes equal to XOR. So this is basically equivalent to XOR. But this is 3 input XNOR function. So obviously both are not same. Okay, both are not same. And hence we say that XNOR gate is not fully associative, or to be more precise, we will say that this is not associative. Okay, so is it associative? No. Okay, just because these two guys are equal, we can't call it as but fully associative. It has to be also equal to the last term, which is not true in this case, and hence XNOR is not fully associative. Okay, and coming to basic identities, the basic identities here will be complement as compared to the previous case. So in case of XOR, whenever one of the input is 0, it functions as buffer gate, but now it functions as NOT gate. In case of XOR, whenever one of the input is 1, it functions as NOT gate, now it functions as buffer gate, and so on. Okay, and so on. Whenever inputs are equal, output is 1. So since XNOR gate is finding out whether the inputs are equal or not. We call XNOR gate also as nothing but equivalence gate. Okay, so due to this reason, we call XNOR gate also as nothing but equivalence gate. Okay, so XNOR gate is also called as equivalence gate because it is finding out if the inputs are equal or not. Or one more meaning is basically equality detector. Okay, the other name is nothing but equality detector, etc. Right? Next, we will do a small discussion on 3-input XOR as well as XNOR gates. So I'm having ABC inputs. Simply count the number of ones. Okay, I'm writing it on the side here. How many number of ones we are having here? In the first case, we are having basically 0 ones. Here we are having 1 1 1 1 2 ones. I see 2 ones here. 1 1 2 ones 2 1 and lastly 3 ones. Now decide whether they are even or odd. Depending on that, we can write here either 1 or 0. Okay. In the first case, even number means 0. Odd number 1, odd number 1, even number 0. Odd number 1, even number 0 0. Lastly, we are having odd number 1. So this is about 3-input XOR function. And what about 3-input XNOR gate? It is simply complement of 3-input XOR. So simply complement it. What do you get? 1 0 0 1. Okay, and then we have 0 1 1 0. Okay, and do remember 3-input XOR gate in the form of minterms as well as maxterms. Okay, it will greatly help you in problem solving in exams because XOR XNOR is one of the most commonly asked questions in exam. Okay, so yeah, whenever we have a 3-input XOR gate, A XOR B XOR C, okay, we can write it as sigma minterms. So minterms corresponds to ones in the function. So we have 4 ones in the function. What are they? The 4 ones we have in the function basically are. Here you can see here this is the 1, this is the 1, another one here, another one. Okay. So they corresponds to what? They corresponds to what? If you notice 0 0 1 means index number 1. Then the next one corresponds to 0 1 0, value is 2. So index number 2. Next, the next one is basically 1 0 0, index number 4. And lastly, we are having triple 1. Triple 1 means index number 7. So 1 2 4 7. Do remember this number. 1 2 4 7 is the representation of XOR gate in the form of minterms. Okay. Yeah. So this is regarding the 3-input XOR as well as XNOR gates. Right. Next. Yeah, this is the topic that I wanted to discuss today. It's one of the most important topics in today's discussion. So whenever the inputs to a logic gate are functions, okay, let us see some questions wherein the inputs to the logic gates are functions. See here, if I ask you what are the inputs to logic gates, we have a logic gate question here. The input to a logic gate is variable, right? Yes. So this is one kind of a scenario. There are other scenarios where the inputs to logic gates are basically functions. Here look at the inputs to logic gates. There is AND gate. The input to AND gate is neither A or B, but rather it is functions F1, F2. Wherein functions F1, F2 are basically functions of a few variables. Here I can see that on the basis of the function given to me, I have index number up till 15. So means F1, F2, F3, they are 4 variable functions. Okay, they are 4 variable functions. And the output of that particular some other circuit is given as input to this particular logic gate. So you have to understand that before this there is some other circuit which probably has inputs of A, B, C, D. And what is this? This is basically function of A, B, C, D. And the output of this circuit is given as input to this AND gate. Okay, so you have to visualize that this is how the data is given to you. So whenever data is given in this manner, how you are supposed to solve these kind of questions. Very important, very, very useful to you in order to solve the problems. Okay, so let's look at this kind of problems. So we will discuss 3 scenarios here. One is AND gate, one more is OR gate, and lastly we are having XOR gate. So these three cases we will discuss what will happen in all the three cases. Okay. So in the first case, I'm taking the gate as basically AND. Taking AND gate. The inputs are F1 as well as F2. The output is nothing but F. Next case I'm taking OR gate. Inputs are F1 as well as F2 and the output is F. And in the last case we are taking XOR gate. Okay, inputs basically are F1 as well as F2, output is F. So like I've told, the first one is AND gate, the second one is OR gate, the last one is XOR gate. Okay, so we are taking here in last case XOR gate. Right? So in the first case, whenever we have AND gate scenario, we can express now output in terms of minterms. So in this case, what happens is minterms of F is equal to the common minterms that you have in F1 as well as F2. Okay. Next, what is OR gate scenario? In this case, minterms of F, minterms of the function F is equal to merged minterms. We have to merge both the lists of minterms. Merged minterms of F1 as well as F2. So in the first case, basically what we are doing is union. Okay, so when I say common minterms, I mean to say we are taking union. This is we are taking intersection. Common means you are taking only those things which are overlapping in the first and second scenarios. So this is basically intersection. And when I say merge, I mean to say union. This is basically union. Okay, union of minterms in the first as well as second function. In the last case, the minterms of F. So if you notice, we are doing the entire discussion only in terms of minterms. So if the data is given to you in terms of max terms, you convert that into minterms and then use it logic. So minterms of F is equal to, this is basically merged minterms minus common minterms. Merged minterms minus common minterms. Obviously, of F1 comma F2. Here also of the functions F1 as well as F2. Okay, so basically this is now union minus intersection. So in the last case, what you are doing is basically, so this is union minus intersection. Okay, so this is how you solve the questions whenever the inputs to the functions are given in terms of whenever the inputs to the logic gates are given in the form of functions. Right? Very, very important. It will help you greatly in problem solving. Now we look at a few problems on this topic. In fact, we will be using it in many problems in today's session. Yeah, this is a very recent question. In fact, I believe this is 2024 computer science though, but this is a very recent question. So, we have been given two logic gates here, and then the output of both of the logic gates is given as input to the third logic gate. The first gate is AND gate, second gate is OR gate, and the last gate is XOR gate. Okay, so I will call this as G1, and this is equal to G2. So the first gate that we are having is AND gate. So what you are supposed to take is, but the inputs for AND gate are F1 as well as F2. So in F1 as well as F2, let us look at the common minterms. Okay, so I am having F1 here, F2 here. So what are common? 0 is present here, not present here, not common. 2 is present here, not present here, not common. So definitely, yeah. Here you can see 3 is common in both cases. 3 is common in both cases. 5 is also common. 7 is also common. 7 is also intersection. And then 8 is present only in one function, not in the second function. 11 as well as 13 are present in both of the functions. 15 is present in F2 but not in F1. So here if you notice, you have taken intersection of minterms. And those intersection of minterms becomes equal to the minterms of output. So now I can express G1 to be equal to, this is sigma min terms. Sigma min terms, yeah, we have 3, 5, 7, 11, 13. So this is 3, 5, 7, 11, 13. So please notice that whenever you use this approach, problem solving becomes very simple. Next, G2. Okay, next we have G2. So this function is basically G2. But this is OR gate. So in OR gate, what we are supposed to do is we have to merge both the midterms. So G2 is equal to sigma midterms. Yeah, what is the list we have? 0, 1, 4, 11. I have to merge both. 0 is common in both. 1 is present here. 1. 2 is present in the second function. I am taking 2 also. And after that, we are going in the increasing order. After 2, we have 4 here. 4. And then we have 6 here in the second case. And lastly, 11 as well as 30. So 11 as well as 30. Okay. So this is basically G1, G2. So we have made use of both of these expressions. Okay. So finally we have got G1, G2. Lastly, I am supposed to get Y. What is Y equal to? Y is equal to, since it is XOR gate, it is merged minus common. That is union minus intersection. So when you take union of both, you get sigma min terms. Yeah, merge both of them. When you merge both of them, we have 0, 1, 2 here, 3 there. So 0, 1, 2, 3. And after that, 4 here, 5 here, 6 here, 7 here. So 4, 5, 6, 7, comma. 8, 9, 10 you don't have. 11 is common, 13 is common. So 11 is present as well as 13 is. Okay. So I simply merged both the lists. I have merged both the lists. 11 here as well as 13. Okay. Minus sigma min terms. Now you have to take intersection. So let us observe what are the intersecting terms. So 0, 1, 2, 4 is present only here, not there. 7 is here, not here. 6 is here, not there. The common terms are 11, 13 here as well as 11, 13 here. So that is the intersection portion. So yeah, I am taking the intersection portion, right? So the intersection portion is basically only two terms, 11 as well as 13. And like I told you, this basically is intersection. And whereas G is basically union, and whereas this is union of its corresponding inputs minus this is basically intersection. So when you take union minus intersection, two guys are gone. 11, 13 are gone. So the remaining midterms that we have right now is the final. So this is pretty much a logical question if you notice. There is not much of calculation, and this was asked for 2 marks in fact. Very simple question asked for 2 marks. But if you know the logic, you can solve it in hardly a few seconds of time. It won't even take a minute of time. It will take less than a minute of time to solve this question in examination. Yeah, so we have sigma min terms. What is the list now? 0, 1, 2, 3, 4, 5, 6, 7. All 8 guys. 0, 1, 2, 3, 4, 5, 6, 7. So this is the min terms representation of the function. So if you notice 0, 1, 2, 3, 4, 5, 6, 7, we have options. We have options here. Okay. And also, if you notice the option D, it is in pi format, which is nothing but product of max terms format. So if 0 to 7 are nothing but min terms, what are max terms? The remaining index numbers are basically max terms. So this is also equal to product of max terms. Remaining index numbers. So we have a 4 variable function. I can clearly see here. 0 to 15 are the index numbers. Wherein 0 to 7 are min terms, means 8 to 15 are max. So 8, 9, 10, 11, 12, 13, 14, and lastly 15. All these are max terms. So hence, even D is the correct answer. Okay. So this is a MSQ question, and in this case, we are supposed to find out how many options is or are correct. So we have 2 options which are correct, which are C, D. Is that clear? Simple question if you know the logic. Okay. Next, we'll solve another similar kind of a question. Again, we have been given functions f1, f2, f3, and you are supposed to find out the output f here. So let me call this output as nothing but G. Okay. So what is G? G is the output of AND gate. Inputs are F1, F2. Okay. So what is G here? G is basically, you guys tell me what is the answer for G. Please tell me what is the answer for G. You guys should use the same logic and tell me what is the answer for G. What is the answer for G here? Yeah, please tell me. No, I don't want the answer. I just want G here. G list of minterms. What are the minterms for G? Simply tell me what are the minterms for G. G is 2, 8, 14. 2, 8, 14. Good, correct. 2, 8, 14. Correct. Nice. Yeah. So again, what you are supposed to do? You are supposed to take intersection of minterms. So go from minterm to first minterm to other minterm. 0 is present here, not present here. So 0 will not be present in the list of G. 2 is present in both cases. So 2 I am supposed to pick. Highlight 2. 5 is present only in one function, not in both functions. 3 is present only in one function, not in both functions. 6 again same story, only one function. 8 present in both functions. 14 present in both functions. So I am supposed to pick only those minterms which are present in both functions. And hence the answer for G is sigma minterms. This is sigma minterms 2, 8, 14. Okay. Now you are supposed to XOR that result G with F3. So what is the answer for F? Merged, that is union minus intersection. When you take union of F3 as well as G, what do we get? We get sigma minterms, union, first union. We'll go in the increasing order. 2 as well as 2. So 2, we have 7 here, so I'm taking 7. Even if the number is present in one list, you are taking simply union, you are simply merging both the lists. So it need not be present in both the lists. 2, 7 and then 8 is present here. 11, 14. Okay, 11, 14 is common again, 14. Minus sigma minterms, we have to take intersection. What is the intersection? 2 is present, so intersection terms basically are 2 here, 14, and as well as the same numbers here, 2 as well as 14. So 2 and 14 are intersection minterms in case of F3 as well as the G, which are inputs of this XOR. And hence basically I can write it as 2, 14. And what is the answer now? See, 2, 14 is cancelled out in both cases. 2, 14 is gone. Then all you have is basically now, all you have is sigma minterms. We have sigma minterms 7, 8, 11. So we have 7, 8 and 11. That's basically the function F. So we have the answer. Option A is basically sigma minterms 7, 8, 11. Okay, so we have got the correct answer. Yes, I think one person got the answer correct. Akhilnath got the answer correct. Okay, good. So it's a very simple question, but please understand this approach is not just used in these kind of questions. Wherever you find the formula approach being lengthy, so definitely you can always prefer this method wherein you are writing everything in terms of minterms format. I will show you one such question. show you one such question where data is given like that. Yeah, in fact, you can use this method for this question. Solve this question. Please solve this question. Half of the question you can solve it on the board itself. By the way, whenever you see this symbol, no, it is bubble. This is a bubble, and hence it indicates NAND operation. Okay. So x, what is x now? X is basically here. X is basically NAND of PQ. So this is PQ whole bar, which is equal to P bar plus Q bar. Okay. And then what is y? Y is basically OR of PQ. So this is P plus Q. This is P plus Q. And then what is Z? Z is equal to multiplication of both because AND gate. So it is x into y. So substitute x and y. We have P bar plus Q bar into then we have P plus Q. Okay. Yeah. So then what do we have? We are having P bar into P. Then you expand, and then we have Q bar into Q. Plus we have P bar into Q plus we have P into Q bar. See, obviously these two guys are how much? This is 0. This is also 0. And then 0 into anything is nothing but that same term. So we have lastly P bar Q plus P Q bar. And what is this? This is XOR. This is XOR. So I can write it as P XOR Q. This is P XOR Q. This is in the form of XOR logic, A bar B plus AB bar logic, right? And now you are XORing that with respect to Q. Okay, and finally, what is the answer now? Finally, the answer is nothing but M becomes equal to now. Now M becomes equal to Z XOR with R. But what is Z equal to? What is Z equal to? Z is equal to P XOR Q. So this becomes equal to P XOR Q. Okay, XOR R. So this is the answer. So if you look at the options, the answer is nothing but D. Answer. Okay. So we have a similar kind of a question again. A similar kind of a question wherein we have to solve that question by using the logic that I described just now. I'll just go for the question. I think I missed that question. I'll share it with you later on. But yeah, nevertheless, even for this question, we can use that logic. Okay, solve this question now. Solve this question. There are many ways of solving this question, but I will show you the simplest way of solving this question. Try to solve this question. So here we have a majority gate, something called as majority gate defined by this equation. This is an equation defining that particular majority gate. So I can say that M becomes equal to AB plus BC plus AC. If the inputs are ABC, right? Okay. So then, what is M of A, B, C bar? That is what I have here. If I have variables as A, B, C bar, in that case, what is that equation? That becomes equal to, this is basically AB plus BC plus AC. Only thing is C is complemented, so we have AB plus BC bar plus AC bar, right? Now the thing is, we can write these in terms of minterms. If you write this in terms of minterms, the expression becomes very simple for you. So let us convert them into minterms format. So I'll do it separately. So I'll move this first. So basically this is M of ABC. So convert everything in terms of minterms, this problem becomes very easy for you. M of ABC becomes equal to, as per this expression, AB plus BC plus AC. In terms of minterms, what is this function now? This is basically 1, 1, x, 1, 1. I am taking ABC order here, please notice. A is there, B is not there, C is there, 1, x, 1. So accordingly, what are the numbers here? 110, 111 means 6, 7. And this is 011, 3, 111 means 7. This is 101, 111, 5, 7. So we have the first expression basically as, this is sigma midterms. Okay, 3, 5, 6, 7. So we have 3, we have 3, 5, 6, 7 as the first function. Okay. Next we have M, A, B, C bar. All I am doing is I am replacing C with C bar. So what will be that expression? AB plus BC plus AC. Only thing is C is complemented, so AB plus BC bar plus AC bar. Again write this in terms of midterms. When you write this in terms of midterms, we get 1, 1 x, and this is x 1 0, and this is 1 x 0. Okay. So accordingly, what are the numbers here? 1, 1 0 means 6, 7. This is x 1 0. 0 1 0 is 2. 1 1 0 is 6. This is 1 0 0 is 4. 1 1 0 is 6. So we have the list of minterms here. What is the expression in terms of minterms format? This is sigma minterms. We have 2, 4, 6 is common, 7. So this is 2, 4, 6, 7. Right? Here I have m of ABC whole bar. So I have to complement. So if this is m of ABC, what is m of ABC whole bar? Whenever you take complement, minterms becomes max terms becomes minterms. Okay. So for this function, what is the list of max terms? What is the list of max terms? The list of max terms is product of max terms. Everything apart from 3, 5, 6, 7. Apart from 3, 5, 6, 7, what do we have? We have 0, 1, 2, and then 4. So like I have told, whenever you take complement, ones becomes zeros and zeros becomes ones. Ones means minterms, zeros means max terms. So minterms becomes max terms becomes minterms. And hence n bar becomes equal to sigma minterms. In the previous case, whatever is the max term now becomes minterm. So 0, 1, 2, 4 now becomes list of minterms. Right? So this part is taken care of, this part is taken care of. Anyway, C is usually taken care of. But we will write C also in terms of minterms, having 3 variables. So I can write C as nothing but x1. Okay, because AB is missing. Usually we have to take ABC variables, right? AB is missing, and hence I have taken 2 x terms here. So when I substitute xx as nothing but 0, 0, 0, 1, 1, 0, 1, 1. I am doing all the 4 substitutions here for x terms 0, 0, 0, 1, 1, 0, 1, 1. Then accordingly, what are the numbers we'll get here? What are the list of index numbers we'll get here? 0, 0, 1 is 1, 0, 1, 1 is 3, 1, 0, 1 is 5, 1, 1, 1 is basically 7. See, the beauty of this approach is nothing but I am not taking any expressions. I am taking only numbers here. Entire problem I am solving by using only numbers. Okay? So now I have obtained everything. First one, second one, third one. Let me call each of them as nothing but maybe this is called as x, this is y, and this is z. Okay, I am taking the first, second, and third terms as nothing but x, y, z. Then what is m of x, y, z? M of x, y, z becomes equal to, on the basis of this formula, x into y plus y into z plus z into x. Okay, z into x. So this is basically the function x. This is basically the function x, the first one. And this is basically the function y. And this is basically the function z. So please notice, if you have these three in mind, now you have to take multiplication of two functions given in terms of minterms format. So whenever you have two functions given in terms of minterms format and you are logically multiplying both of them, all you have to take is common minterms. So in x and y, what are the common minterms? 0 is present here, not here. 1 is present here, not here. 2 and 4 are present in both places. So x and y basically now can be written as sigma minterms xy. Okay, so this is basically written as sigma minterms x comma y. Okay, so all I am taking is nothing but common minterms in x as well as y. Okay, sigma minterms 2, 4. Then what about y and z? So let us take y here, z here. So in case of y and z, 1 is present here, not here. 3 is present here, not there. 5 is present here, not there. 7 is present in both cases. So it is sigma min terms only 7. This is for y z. Okay. And what about for zx? Zx. So first and last, common min terms. 1 is present in both cases. 2 is present here, not here. 4, yeah, I think apart from 1 there is nothing else common. So there is only sigma min terms. This is sigma min terms. We have 1. That's it. So this is basically the min terms expression. Next, what do? You are taking logical addition. Whenever you take logical addition, you have to merge all. So let us merge all. When you merge all I get is nothing but I have 1, 2, 4, 7. So I have 1, 2, 4 and 7. Do you remember this particular expression? We have earlier seen this. This is one of the most, I told you, commonly asked logical functions. Yeah. So do you remember? 3 input XOR gate is nothing but 1, 2, 4, 7 min terms. Now also what did we get? We got the same list of min terms. Okay, we have got the same list of min terms. Here also I got that same list of min terms. So once you remember that, now straight away you can say that, yeah, this is basically 3 input XOR gate. This is basically 3 input XOR gate. Okay. See, the beauty of this approach is nothing but nowhere here we have taken expressions. We have discussed the entire problem only in terms of numbers. Now if you solve the problem by using expression format, equation format, yeah, you will get the same answer, but there is a very good probability that you will do silly mistake there, because you have to write lengthy expressions. Okay, you have to write lengthy expressions, and hence if you try to do that by the traditional approach, the brute force method, there is a possibility of you getting correct answer, but the thing is, it will take first of all a lot of time, and you have to be very cautious at every step, because one simple mistake here and there also, your entire expression will go wrong. Okay? Yeah. So be very careful. Use this approach, min terms approach. It will greatly help you in problem solving. Let's go for another problem. Yeah. Here again, all the options are themselves given in terms of min terms format. So yeah. Anyway, this is a simple question only. This is A. A, and this is B bar given as input to the AND gate, and then this is C. Output of this AND gate is called B bar into C. Then what is Z? Z is equal to now A plus B bar C. That's it. We have got A. But only thing is we have to express the answer in terms of min terms format. So how do you express the answer in terms of min terms format? Look at the order always. Order is ABC order. So since it is ABC order, how do you write A as? A I can write it as nothing but 1XX. And how do you write B bar C as? A is not there, first term, X, B is complement format and C is true format, 0, 1. Now let us substitute X values as nothing but zeros and ones. So here what do we get? 1 0 0, this is basically 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay, so we'll get 4 min terms here. And we'll get 2 min terms here. What are they? 0 0 1 and then 1 0 1. And write them in terms of index numbers, that is decimal values. What are the decimal values for all of them? The decimal value here is 4, this is 5, this is 6, and lastly this is 7. And here this is basically 1 and this is 5. Okay. So now since you are taking logical addition, you have to merge both list of min terms. So let us merge both list of min terms. When you merge both list of min terms, we get sigma min terms. Yeah, we have 1 here. And then 4, 5, 6, 7, 5 is common in both cases. So 1, 4, 5, 6, 7. This is the list of min terms. So all options are given in terms of min terms only. And the correct answer is nothing but D. Okay, 1, 4, 5, 6, 7 is the correct answer. This is pretty recent question. Okay, pretty recent question. One more question. So not a tough question. So all you have to do is nothing but write the expression. And after writing the expression, use the Boolean principles. That is representation of Boolean function rules. And then write that function, convert that product terms, individual product terms into min terms, and get the answer in terms of min terms format. Okay? Yeah, next. Yeah. So please solve this question. Try to solve this question. Again, you have to express the function in terms of, if you look at all the options are in terms of min terms only. Okay? What is a min term? Min term is a product term consisting of all variables either in the true form or complement format. Here, every option has 2 product terms, and each product term has all the three variables x, y, z. They may be in true format or complement format. X may be in true format, x bar or x in true form, I don't care. Both of them are present basically. Okay? Yeah, so please get the answer here. So here, this is nothing but x, y bar. Yeah, this is basically so here basically we have x bar y plus x y bar. That is the output of XOR gate, right? That is basically the output of XOR gate. X, y bar. Okay. Since it is AND, we'll try the normal method first, and if it does not work out, then we'll go for the minterms format. Then what about this guy? Here, please notice the input is nothing but x bar y plus x y bar. Okay, so for XNOR function, what is the logic? The XNOR function logic is nothing but complement both inputs. Okay, complement both inputs first, or this is also equal to x XOR y. Okay, x XOR y. So this can be written as first term, which is z complement, into second term complement, which is x XOR y whole complement, plus multiply both the inputs. The first input is nothing but z. The second input is basically x XOR y. And then you have to take AND of this. So it looks quite lengthy expression as such only, but nevertheless we'll try it out. I'm pretty sure that this is quite lengthy expression and slightly confusing expression also. Z bar into, what is this guy? This is x bar into y bar plus x into y. First term. And second term is basically z into what is x XOR y? X bar y plus x y bar. Okay, x y bar. And anyway we are also having z, I'm taking z here. Okay, so we have got two terms, and then we have to multiply this expression as well as this expression. Notice now we have four terms here, we have two terms here, and we have to multiply them. It becomes quite lengthy expression. As such, you will not, it's not that you don't get the answer, you will 100% get the answer, but only thing is there is a lot of calculation involved here, which make a lot of time for you, which may take a lot of time for you. What is the better method? Like I've told, the better method is basically the minterms format. So let's go for the minterms format. Like I've told, it's not that you don't get the answer, you will get the answer, but only thing is, in exam we don't have that much space also in the rough sheet that will be given to you. It's a small sheet given to you, so you don't have that much luxury of space also. First, yeah, anyway we can write it as basically x bar y plus x y bar. Initially I am writing the expression, but now converting that in terms of minterms. What is this in terms of minterms? When I take x, y, z as the variables, so this becomes equal to 0, 1, x. This is 1, 0, x. That's it. With practice, now we can directly write the function in terms of minterms. What is the list of minterms we have? 0, 1, 0. That is nothing but 2. And then we have 0, 1, 1, 3, 1, 0, 0, 4, 1, 0, 1, 5. So I have x bar y plus x y bar as nothing but sigma minterms 2, 3, 4, 5. That is given as input to this particular XNOR gate. I will split this XNOR gate into XOR followed by NOT gate. Followed by NOT gate. I am splitting this into two parts here. Please notice. Okay. So I am removing the bubble and then taking a complement separately. I am not disturbing this entire thing, but only thing is I am writing this as two parts. I am splitting this into two parts so that my problem solving becomes easy. Okay. Yeah. So how do you write Z in terms of minterms format? Z in terms of minterms format is basically x is not there, y is not there, z is in true form 1. See, whenever LSB is nothing but 1, that corresponds to all odd number of minterms. Okay, so what are the odd number of minterms we have in a 3 variable function? 1, 3, 5, 7. So I can take now z in terms of minterms format as nothing but 1, 3, 5, 7. So what is the XOR operation here? First of all, this is XOR operation. So XOR means merged minus common. When you merge both the list of minterms, what do we get? We get the expression as this is sigma minterms. We have 1, 3, 5, 7 here, 2, 3, 4, 5 here. So 1, 2, 3, 4, 5, 7. This is merge. Minus what is common? 3, 5 is common. Sigma min terms 3, 5. Okay, so if you remove 3, 5 here, 3, 5 here, then this is a new method, I agree, but rather with practice, this becomes one of the most comfortable approaches for you. In the beginning, every new method is a tough method, but with practice, it becomes easy for you. Yeah, I have got here expression as nothing but 1, 2, 4, 7. When you complement that, what is the list of min terms here? Sigma min terms. Apart from 1, 2, 4, 7, everything else, which is basically 0. So 1, 2 is there, 3, 4 is there, 5, and lastly 6. Okay. Now you have to take AND of these min terms as well as the min terms that we have here, which is 2, 3, 4, 5. And when you take the function here, then what do we get? Only common things you have to take. What are the common things in both of the inputs? Yeah, I think 3, 5. 3, 5 is common. 3, 5 is common. And hence now the answer finally becomes equal to sigma min terms 3, 5. Now you have to express that 3, 5 min terms as expression format. What is 3? 0, 1, 1. And hence this is basically x bar y z. And what is 5? 5 is 1, 0, 1 x y bar z. That's it. We got the list of min terms as nothing but x bar y z plus x y bar z. So if you look at the options, I think the correct option is A. The correct option is A. Okay. So if you see in this method also I have solved the entire problem only in terms of min terms format. And I didn't write any expression also. So it looks very clean also. There is not much of calculation involved here because I am writing everything in terms of numbers instead of the variables. So if you write everything in terms of variables, you will get the answer, but rather you will end up doing lengthy calculations. But in this approach, all you have to deal with is numbers. So dealing with numbers is much more comfortable, much more less error prone. Okay, much more less error prone as such. Okay. Yeah, let us solve a few more questions. This is a simple question. All you have to do is identify the logic gates in this scenario. Okay. So here I have a NOR gate. What is the output of NOR gate? The output of NOR gate is basically add the inputs and then complement it. Now I can apply De Morgan's theorem here and I can write this as nothing but this is C bar into D bar. Okay. And you have been given that y is equal to this is AB first term plus C bar D bar. Okay, C bar D bar. I can clearly see that I already got C bar D bar here. So the C bar D bar as well as C bar D bar here can be equated. If you equate both of them, whatever is AND operation you are having here is basically G2. Okay, sorry, whatever plus operation you are having here is basically G2. Means I got G2 here. What is G2 logic gate? G2 is nothing but OR gate on the basis of that. And then the other input for the gate G2 has to be AB input. So accordingly, this output should be equal to AB. The second input of G2 is basically output of G1. The output of G1 has to be equal to AB. But for G1, what are the inputs? The inputs are basically A bar as well as B bar. Now let us go for option verification. So in how many cases you are having, gate 2 as nothing but OR gate, you are having in 2 cases. So the answer has to be either option A or option C. Okay, option A or option C. So let's choose option A. In option A, the gate is nothing but NOR gate. So if this is NOR gate, let's assume. Okay, if this is NOR gate, let's assume. If I verify A, if A is the correct answer, I'll mark A. So if A is the wrong answer, I can definitely directly mark option C and go to the next question. So let's verify. So I want output as nothing but AB when the inputs are nothing but what? When the inputs are A bar and B bar. So if it is NOR gate, I have to first of all add both the inputs and then take complement. So if I do that, what is the output? I'll apply De Morgan's theorem. I'll get A bar whole bar into B bar whole bar. A bar whole bar is nothing but A and B bar whole bar is nothing but B, and I got AB. So correct answer. So means when I choose the answer as nothing but option A, in that case I got definitely the output of that gate as nothing but AB. So means definitely I can say that yeah, A is the correct answer. So I don't even have to cross verify options. Okay, C need not even be verified. In fact, I got the correct answer as nothing but A in this time. Okay. this is one kind of question you are getting in the recent times. Examiner is trying to scare you by giving a lengthy diagram. Okay, the diagram is not very big, but rather it looks scary. Okay, they intentionally zoom it out so that it looks like a big diagram for you. Okay, now according to scale, this diagram looks even more bigger in exam paper. So this is just to scare you, but as such the question is not tough, it's a very easy question. So you have B input, means this guy is basically B bar, okay, and this is also equal to B bar, and this is equal to A bar, and this is equal to A. So this is NOR gate. So for this NOR gate, what are the inputs? A bar, B bar. So what is the output now? Output is nothing but A bar plus B bar whole bar, which basically becomes equal to, by applying De Morgan's theorem, A into B. And what about here? What about here? Here the output is basically A, one of the input is nothing but A, the other input is plus B bar whole bar. And by applying again De Morgan's theorem, what do we get? We get the output as nothing but A bar into B bar whole bar. B bar whole bar is basically B. Okay? And then we have another NOR gate here. So since this is another NOR gate, what is the function here? First of all, you have to add both the inputs. What are the inputs? One input is nothing but A bar B, and the other input is A into B. A bar B into A into B whole bar. So when you add both of them and take B common, A is eliminated. So if I take B common here, I get A plus A bar. Okay, and then whole bar. So A plus A bar becomes equal to 1. So we have B into 1 whole bar, and finally the answer here is nothing but B bar. Okay, that's it. I've got the answer. The answer is nothing but basically B bar. So is it not a simple question? Yes, but sometimes it looks scary because the diagram is disproportionately expanded, zoomed in, so that it looks like a big diagram for you. Okay, diagram may look big, but rather the circuitry is not as such big. It's very simple. We only have used, I think, probably some 4 or 5 logic gates. So 4 or 5 logic gates means not a tough question, not a lengthy question. Okay. This was a good question. I will give you logic for this question to you, and I want you guys to solve this question. Okay. I'll simply give you logic for this question. This is called as, in the context of digital circuits, something called as stuck-at fault. We call it as basically stuck-at fault. And as a designer, it is your duty to identify this fault. Okay. So where is the fault present here? The line T in the following figure is permanently connected to ground. This is basically a fault. Okay. So this is basically a fault. Now this is ground connection. So since this is always connected to ground, the T value is always 0 irrespective of the inputs that you apply. Okay, irrespective of the inputs that you apply, the value of T is always equal to how much? It's equal to 0. And hence, the output of the circuit will not behave as expected. And you have to identify, the fault by applying some combination of inputs. And the logic in this question is nothing but we will construct this table wherein there are 2 columns. Yeah, the first column is nothing but variable combination. So how many variable combinations we will have? Starting from all zeros to all ones, we will have 16 variable combinations. We will have 0, 0, 0, 0. Double 0, double 1. So we are taking all 16 combinations. See, even in examination hall, this is your task. This is one method. I'll show you other method also. This is a more traditional method. So if it is given as MSQ question, this will not fail you. And lastly, all 4 inputs. Yeah, starting from all zeros to all ones, we have taken all combinations. Okay, we have taken all combinations. Now let's assume there is no fault. If there is no fault, what is the value of output? So that is what we are supposed to identify. And for that, what I am doing is I am writing this as nothing but basically min terms format. So in min terms format, what is this expression? This expression is basically the first one. So this can be written as This is x1 plus x2. Writing it directly basically. So we can write this as x1 into x2 into x3. Okay, so this is NAND gate whole bar, which can be equal to x1 bar plus x2 bar plus x3 bar. And then what about this guy? This is basically x1 bar plus x2 bar plus x3 bar, which is basically this expression. This becomes equal to x1 bar plus x2 bar plus x3 bar. Okay, by applying De Morgan's theorem. And the other variable for this is basically x4. So plus lastly x4. Okay, and then what is t equal to? What is t equal to? T is equal to, we get x3 plus x4. So this is x3 plus x4. Okay. And finally, what is the value of output? The overall output value. If I call the output as nothing but y, what is the value of y now? Y, assuming that there is no fault. If there is no fault, what is the value of y? The expression is x1 bar plus x2 bar plus x3 bar plus x4 bar plus the first one. What is the second one? Sorry, this is AND gate. I'm sorry, this is AND gate. My mistake. So since this is AND gate, we can write this as this is x3 x4. Okay, so plus x3 into x4. Okay, and then you have to take whole complement of this. So this is a function. So here we can use some basic theorems. One of the theorem I can use is nothing but RLR, which states that a plus a bar b becomes equal to a plus b, or the RLR applied in a different format is nothing but a bar plus ab becomes equal to a bar plus b. Okay, these are a couple of Boolean laws. So I am having one such expression here. So if I take x3 bar plus x3 x4, I can write it as what? Now I can write it as this expression. So this is equal to x1 bar plus x2 bar. So I am applying RLR here, plus x3 bar plus the last one x4 bar. In this term, x3 will be gone. Okay, so in this term, by applying the RLR, x3 will be gone. So if x3 is gone, the remaining expression becomes equal to simply this is x4 whole bar. And finally we have the expression as x1 bar plus x2 bar plus x3 bar. See, x4 bar plus x4 bar plus x4 becomes how much? This becomes equal to 1. Okay, so 1 plus anything becomes equal to 1. I think there is a small mistake, data mistake in what I've done probably. It looks like there is a small data mistake in what I've done. Because you are getting the answer as nothing but simply 0 even without fault. And without fault you are getting the answer 0, it should not occur. Okay, we'll apply another logic. Like I've told, there are many methods of solving this problem. Let's go for the second method. The second method is option verification. Okay, second method is option verification. In all these cases, what I'm doing is nothing but in all the options. Okay, I'm taking the variable combination that is nothing but x1, x2, x1, x2, x3, and x4. I'm taking the combination of variables. And then I am analyzing the scenario what happens without fault. Okay, what happens without fault and what happens with fault. And when can you identify the fault? You can identify the fault whenever the values without fault and with fault are different. If those values are different, the expected value and the value that you actually obtain both are different. So when both are different, it means that it is a fault. Okay, so this is basically the expected value. Without fault means basically expected value. Okay, and with fault whatever you get is nothing but actual value. Actual value. And whenever expected value is different from actual value, it means that there is a fault. Okay, so we can say that fault occurs whenever expected value is not same as actual value. Or in fact, you can also solve it by means of this table also. Like I've told, this is more traditional approach. Here also this part you have to do. I want you guys to do this part. We have to get expected value here, as well as also we have to get here expected value. Actual value. You have to complete this table. This is homework for you. Okay. So here I will apply all the four combinations. The first combination is what? 0, 0, 0, 0. Option A. Okay. So let's apply these values. 0, 0, 0, 0. When you apply these values, what do we get? So let's apply. This is 0, 0, 0, 0. NAND gate, one of the input is nothing but 0. Output is what? 1. And then for OR gate, one of the input is 1. Output is also equal to 1. And for NOR gate, one of the input is 1, means output is equal to 0. This is a scenario without fault. Okay, so what is the expected value? Expected value is nothing but 0. Let us see what is the actual value. Actual value is nothing but this is grounded, so this is 0. So since this is 0, still I don't care, because the output is 0 because of this path, not because of this path. So now also with fault also, with fault scenario also, 1 plus anything, whole bar becomes always equal to 0. So in this case, what is the actual value? Actual value becomes equal to 0. Okay, so obviously fault cannot be detected in this case, because both values are one and the same. So I can't decide whether there is a fault or not on the basis of this. Okay. So next we have 0 111 as the option B. So let us apply 0 111. Okay. So next case we have 0 111. So I am taking this 0 111. 111. Yeah. So again, NAND gate, one of the input is 0, output is 1. OR gate, one of the input is 1. Sorry, one of the input is 1, means output becomes 1. For a NOR gate, one of the input is 1, means definitely output has to become equal to 0. So since this is NOR gate, output is now also equal to 0, and output is 0 because of this path. So due to that, expected value is 0, and even with fault, the answer is nothing but 0. Because even with fault, yeah, this is shorted, but will it matter? Will it matter for the output? No, because output is 0 because of this part. Okay. So next option C. We have to verify the other option. What is the option C? Option C says all four ones. 1, 1, 1, 1. Okay. So let us go for option C. So in this case we have 1, 1, 1, 1 as the input. All four ones. Yeah. For a NAND gate, when all inputs are ones, output becomes equal to 0. So this is 0. But this is OR gate. OR gate, one of the input is nothing but 1. When one of the input is 1, definitely output becomes equal to 1. And for NOR gate, one of the input is 1, means output becomes equal to 0. So now also, yeah, technically 1 into 1 has to become equal to 1. This should become equal to 1 in the expected scenario. But in the actual scenario, what happened? Because of all this became 0. So 1 plus 0 whole bar still becomes equal to 0 only. Okay, so now also what happens is nothing but we will have 0, 0. So means in none of these three scenarios we are in a position to obtain whether there is fault or not. Like I have told, you will identify the fault only whenever the actual value and expected value both are different. But in all the cases, the actual and expected values both are same. So since both are same, yeah, you can't detect the fault, and the answer is nothing but none of this. In none of the four cases, in none of the three cases, we are in a position to obtain whether there is fault or not in the system on the basis of given data. So hence the answer is nothing but none of this. A good question, like I've told, in the context of digital circuit design, we call it as nothing but stuck-at fault testing. And as a designer, you are supposed to identify whether there are any stuck-at faults in your system. There are two kinds of stuck-at faults. In this case, the stuck-at fault is to ground. There is also stuck-at one fault also. Stuck-at one fault is basically shorting a line and VCC. So if there is a short between a line and VCC, so in that case we call it as nothing but stuck-at one fault. Okay. I think guys there is audio. Okay. Yeah, so these are some of the important questions on logic gates. Yeah, there are more and more questions, but rather, like I've told, this approach, the last approach that I've discussed, wherein solving the questions by using minterms. Okay, solving the questions by using minterms. This is one approach. I always suggest for students. And there are other questions also I wanted to discuss. I think I'll take another session for this logic gates topic to cover the remaining questions. Yeah, this method. Okay, this method wherein the inputs to AND gate, OR gate, XOR gate are given in the form of functions. So in this case, what you can do is nothing but, yeah, in case of AND gate, all you have to take is intersection of minterms. In case of OR gate, you have to take union of minterms. In case of XOR gate, you have to take union minus intersection of minterms of inputs. Okay, and this approach, you are not dealing with expressions, you are dealing with only numbers. So because of that, problem solving becomes much more comfortable, much more easier, and less error prone. This is very important. Okay, so if you even miss one bar, one complement term also in case of digital circuits, your entire expression will be altogether different term, and it will go wrong for you. So you can avoid those kind of mistakes when you write everything in terms of numbers. When you write everything in terms of numbers, those kind of mistakes you will commit in a very, very less quantity. Okay, so because of that, I always suggest solve the questions. If it is simple question, go for the normal method, expression format. But if the question is a bit lengthy, okay, and after some time it looks very big expression for you, the expression is too long for you, means you are not supposed to follow the expression format. Go for the minterms format in that kind of a problem. Okay. Yeah. So with this, we'll call it a day today. So like I've told, there are a few more questions left out. So because which I'll take one more session for logic gates, probably after the main flow is complete, right? Okay. So if you have any doubts, please let me know, guys. If you have any doubts, please let me know. Okay. Okay, so if there are no doubts, we'll call it a day. Okay, guys, thank you for joining the session. Okay, notes I'll have to update. Okay, I'll update the notes. Probably you can check tomorrow regarding the notes. I'll update in the description below. Okay, so we'll call it a day, guys, and we'll meet tomorrow. In tomorrow's day, we will discuss about multiplexer topic. Okay, thank you all for joining.